Chemical vapor deposition in semiconductor industry. Chemical vapor deposition, or CVD, plays a vital role in the semiconductor industry by enabling the precise creation of thin films essential to modern electronic devices. This process is central to precision manufacturing, allowing engineers to control layer thicknesses and compositions down to the nanometer scale. With CVD, highly uniform and conformal films can be deposited on complex three-dimensional structures, a key requirement as devices continue to scale down in size. It is a cornerstone of thin film technology, producing materials like silicon dioxide, silicon nitride, and metal silicides that form insulating, conductive, or barrier layers on semiconductor wafers. Furthermore, CVD is indispensable to modern electronics, supporting everything from logic transistors to NAND devices and sensors. In summary, chemical vapor deposition is truly the foundation of modern semiconductor fabrication, enabling the advancement of technology across industries. What is CVD? Chemical vapor deposition, or CVD, is a process that transforms gaseous chemicals into solid materials on a surface. In essence, it involves introducing chemical vapors in the gas phase, which then react or decompose to form a solid phase, typically a thin film, on a substrate. This transformation is the cornerstone of modern thin film coating technology. The defining features of CVD include atomic-level precision, enabling layers of material to be deposited one atom or molecule at a time. It also ensures uniform coating thickness across complex surfaces, even within deep trenches or high aspect ratio structures. Another key advantage is the high quality of the resulting materials, often with excellent electrical, mechanical, or optical properties. You can think of CVD as a form of 3D printing at the atomic scale, building materials molecule by molecule with unparalleled precision and control. CVD process overview. The chemical vapor deposition process can be broken down into 4 essential steps. First is gas introduction. In this step, chemical vapors are carefully introduced into the reaction chamber. These gases are the precursors, the building blocks for the thin film. Second, a chemical reaction occurs. Heat and energy are applied to break down these gas molecules inside the CVD chamber. This triggers a reaction that leads to the creation of solid material. The third step is film deposition, where atoms from the reaction begin to settle and form a thin, uniform layer on the surface of the substrate. Finally, byproduct removal ensures that all gaseous byproducts and waste materials are evacuated from the chamber to keep the environment clean. Throughout the process, there's a controlled environment, atomic precision, and a clean process, ensuring consistency, accuracy, and minimal contamination. CVD in semiconductor manufacturing. Chemical vapor deposition is deeply embedded in the architecture of modern semiconductor chips. It enables the formation of multiple thin film layers, over 50 in some devices, with nanometer-level thickness control. These layers include gate dielectrics, which serve as ultra-thin insulating barriers, playing an essential role in minimizing current leakage. Polysilicon gates are another application, functioning as the control elements of transistors. These are critical for device switching and performance. Metal interconnects, used for routing electrical signals between components, are also deposited using CVD, and they are vital to overall chip operation. The impact of CVD on the industry is enormous. About 90% of chip manufacturing processes rely on it. Furthermore, the CVD equipment market exceeds $50 billion annually, underscoring its commercial significance. From smartphones to computers, automotive systems, and IoT devices, CVD technology supports nearly every modern electronics platform. CVD in semiconductor manufacturing, enabling Moore's Law. Chemical vapor deposition plays a critical role in enabling Moore's Law, the observation that the number of transistors on a chip doubles approximately every 2 years. As semiconductor devices shrink in size, maintaining high performance and functionality requires extremely precise deposition techniques. CVD delivers the atomic-level control necessary to fabricate ultra-thin layers with uniformity across increasingly complex and miniaturized chip structures. This ability to deposit high-quality films at the nanoscale supports the continued miniaturization of transistors, a foundational requirement for today's advanced logic and NAND devices. At the forefront of this progress is the current 3-nanometer technology node, where CVD is indispensable for building tiny, densely packed features. Without CVD's precision and scalability, pushing the limits of transistor density and efficiency would not be possible, making it a key enabler of technological evolution in the semiconductor industry. Types of CVD processes. Chemical vapor deposition, or CVD, processes are classified based on two main factors: operational conditions and vapor characteristics. Starting with operational conditions, we have atmospheric pressure CVD, which takes place under standard pressure conditions and is widely used for its simplicity. Next is low-pressure CVD, where the reduced pressure improves film uniformity and allows for better step coverage on complex wafer topography. Lastly, there's ultra-high vacuum CVD, used when an ultra-clean environment is critical. This setup minimizes contamination and supports the growth of high-purity films. Now, let's explore vapor characteristics, specifically how precursors are delivered. In aerosol-assisted CVD, liquid or gas precursors are converted into aerosols, making it possible to use non-volatile precursors effectively. Direct liquid injection, on the other hand, involves feeding liquid precursors directly into the system, enabling high growth rates and precise control, especially useful in advanced semiconductor fabrication. Types of CVD processes. CVD processes can also be classified by substrate heating and plasma methods, both of which affect temperature control and reaction enhancement. In hot wall CVD, the entire reaction chamber is externally heated, ensuring a uniform temperature across the substrate and chamber walls. This method is beneficial for consistent film deposition, but may result in more contamination buildup. Cold wall CVD, by contrast, directly heats only the substrate while the chamber walls remain cooler. This allows for localized heating, reducing unwanted reactions on chamber surfaces and improving throughput. Plasma methods enhance chemical reactions using energetic plasma. Plasma-enhanced CVD, or PECVD, allows deposition at lower temperatures, making it ideal for heat-sensitive materials. Microwave-assisted CVD produces high-density plasma, promoting rapid and efficient film growth. Remote-enhanced methods keep the plasma source away from the substrate to minimize damage. Finally, low-energy enhanced CVD uses gentle plasma conditions to reduce defect formation, enabling precise and delicate processing. Process selection. Selecting the appropriate CVD process is critical to achieving the desired material properties, film quality, and device performance. With more than 12 distinct variants of chemical vapor deposition, each option is tailored to address specific fabrication requirements. The decision depends on a combination of factors: the material system being deposited, substrate compatibility, desired film characteristics, and manufacturing constraints. For instance, high-temperature CVD methods may be ideal for robust materials, but unsuitable for temperature-sensitive substrates. Similarly, when working with non-volatile precursors, aerosol-assisted or direct liquid injection methods offer effective delivery solutions. Low-pressure systems might be chosen for their enhanced uniformity, while plasma-enhanced CVD may be favored for temperature-sensitive layers due to its lower processing temperatures. Ultimately, the key to optimal process selection is balancing technical needs with cost, throughput, and integration requirements within the overall semiconductor manufacturing workflow. Key materials deposited. In semiconductor manufacturing, three major classes of materials are deposited using CVD: silicon, dielectrics, and metals. Silicon forms the foundation of modern devices. Commonly deposited types include polysilicon, used for gate electrodes in transistors; amorphous silicon, ideal for thin film applications like displays; and epitaxial silicon, which creates high-purity, defect-free layers for advanced logic and NAND devices. These silicon materials typically exhibit 99.9% purity and a band gap of 1.12 electron volts. Dielectrics serve as essential insulation layers. Silicon dioxide is used for gate oxides and isolation layers. Silicon nitride acts as a barrier material, especially in preventing diffusion. High-K dielectrics are used in advanced gates to reduce leakage and allow for further scaling. These materials show a dielectric constant of around 9.0 and resistivity exceeding 10 to the power of 16 ohm centimeters. Metals are critical for conductors and interconnects. Tungsten is used for via plugs and contacts due to its high melting point. Copper, with low resistivity, dominates interconnect lines, while aluminum remains in legacy applications. Typical metal deposition occurs around 400 degrees Celsius, with a resistivity as low as 1.7 micro-ohm centimeters. Key materials deposited. In semiconductor manufacturing, precision in material deposition is non-negotiable. Chemical vapor deposition, CVD, delivers the atomic level control needed to build nanometer-scale structures. One of the key strengths of CVD is material precision. It allows for deposition accuracy down to the atomic layer, ensuring exact film thickness and uniformity. This enables consistent device performance, critical in advanced nodes. CVD supports over 50 material types, encompassing a broad range of silicon, dielectric, and metal compounds. These materials serve roles ranging from gate control and interconnects to barrier layers and passivation. Thickness control reaches angstrom-scale precision, with each cycle capable of adding just fractions of a nanometer. Such control is essential for scaling and integration. Additionally, purity levels in CVD processes reach as high as 99.99%, minimizing contamination and improving electrical performance. The combination of atomic scale thickness control and ultra-high purity is what makes CVD indispensable in modern semiconductor fabrication. Advantages and applications. Chemical vapor deposition, or CVD, is widely recognized for delivering exceptional uniformity with less than plus or minus 1% thickness variation across a wafer. This uniformity is critical for achieving consistency in device performance and yield across production batches. CVD also offers precise thickness control, down to atomic scale resolution, enabling nanometer scale engineering for advanced nodes. Another major advantage is ultra-high purity. CVD processes routinely achieve material purities exceeding 99.99%, which is essential for minimizing defects and improving reliability. Additionally, CVD supports low-temperature processing, often as low as 200 degrees Celsius, which helps avoid thermal damage and makes it compatible with temperature-sensitive materials. It also ensures excellent step coverage, meaning it can coat complex 3D structures uniformly. These strengths make CVD a foundational technology in the industry. Its key applications include semiconductor chips, solar cells, LEDs, OLED displays, and protective coatings. Market growth. The chemical vapor deposition, or CVD, equipment market is experiencing significant expansion. As of 2024, the global market size has reached $24 billion, reflecting strong demand across various industries, particularly in semiconductor manufacturing. This growth is driven by increasing complexity in device architecture and the need for ultra-thin, high-purity films. The annual growth rate stands at 8.5%, showcasing the industry's confidence in CVD as a scalable and reliable deposition method. Notably, about 70% of this market is directly tied to semiconductor applications, which include transistors, interconnects, and advanced packaging. CVD continues to be essential in manufacturing leading-edge devices, especially as the industry pushes towards smaller nodes. In fact, CVD processes are playing a crucial role in advanced technology nodes, including the 5-nanometer class and below. These trends highlight the strategic importance of CVD in enabling next-generation electronics. Future of CVD technology. The future of chemical vapor deposition is being shaped by cutting-edge innovation and transformative trends. One major area is AI integration, which is enabling smart process control through automation and predictive analytics. These advancements improve process stability and reduce variability. Meanwhile, quantum materials like quantum dots and graphene layers are expanding the possibilities of CVD for next-generation electronics. These materials require atomic-level control that CVD is uniquely suited to provide. As semiconductor technology scales down, advanced nodes below 2 nanometers are being developed. CVD supports this transition with capabilities for the 1.4 nanometer process and 3D integration, both essential for sustaining Moore's law. Sustainability is also a growing focus, with green CVD processes aimed at waste reduction and improved energy efficiency. The technology roadmap anticipates AI-enhanced CVD in 2024, 2 nanometer production by 2026, quantum CVD by 2028, 1 nanometer nodes by 2030, and molecular CVD by 2035.